This project cost billions of dollars. It took years to build, and some experts believed it should never have worked. But somehow it did. Welcome to Next Gen Engineering. Today, we're breaking down the insane engineering behind this project, step by step. The plane that was never supposed to fly. Aviation and aerodynamics focus, with materials science intersections. Opening hook, the impossible airplane. In 1947, a group of engineers looked at a simple equation and came to a terrifying conclusion. As an aircraft approaches the speed of sound, drag does not increase gradually. It explodes. Visual, graph of drag coefficient versus Mach number showing sharp spike near Mach 1. At around Mach 0.8 to 1.2, shockwaves form across the wing. Air can no longer get out of the way smoothly. Pressure spikes. Lift becomes unpredictable. Control surfaces lose effectiveness. Pilots called it compressibility. Several aircraft attempting to push that boundary went into unrecoverable dives. The prevailing belief among many aerodynamicists was blunt. Manned, controlled flight beyond the speed of sound might be physically impossible. And yet, just a few years later, a bullet-shaped aircraft named the Bell X-1 shattered that assumption. This is the story of the plane that was never supposed to fly, and the physics that made it possible. Part 1. The context. Why break the sound barrier? World War II had ended, but a new arms race had begun. Jet propulsion had already changed aerial combat. Aircraft like the Messerschmitt Me 262 proved that speed meant survival. But speed had a ceiling. At sea level, the speed of sound is roughly 343 meters per second. At altitude, it drops to around 295 meters per second. Why? Because the speed of sound is not about speed. It's about temperature. The equation is C equals square root gamma RT, where gamma is the ratio of specific heats, R is the gas constant, T is temperature. Visual, equation animates, highlighting temperature term. Sound is simply pressure waves moving molecule to molecule. Lower temperature means slower molecular motion, and therefore slower sound speed. By the mid-1940s, aircraft were hitting Mach 0.8 in dives. And that's when things went wrong. Part 2. The physics constraint, the sound barrier. As an aircraft approaches Mach 1, air in front cannot sense the plane coming fast enough to move aside smoothly. Pressure waves pile up. Shockwaves form. Visual, Schlieren footage of shockwave formation. These shockwaves cause three major problems. 1. Wave drag. Unlike regular drag, wave drag increases dramatically near Mach 1. Visual, drag components break down. Parasitic versus induced versus wave drag. Total drag skyrockets. In some tests, drag doubled within a tiny Mach increase. That means engines must produce dramatically more thrust for marginal speed gains. 2. Control reversal. Shockwaves form over control surfaces. This changes the pressure distribution. Pilots would push the stick forward, and the plane would climb instead. 3. Center of pressure shift. The center of lift moved backward abruptly. Aircraft pitched violently nose down. This killed test pilots. The problem wasn't power. It was aerodynamics. Part 3. First principles. Why straight wings fail. Subsonic air flows smoothly around curved surfaces. But at transonic speeds, parts of the airflow exceed Mach 1 locally, even if the aircraft is technically subsonic. This creates localized shockwaves. Straight, thick wings worsen this effect. Why? Because air must travel further over the top surface. To conserve mass flow, it accelerates. An accelerated air lowers pressure, generating lift. But if it accelerates too much, it goes supersonic locally, then slams back to subsonic via a shockwave. This causes boundary layer separation. Visual, CFD simulation showing separation behind shock. Separated airflow means massive drag, buffeting, loss of lift. So the impossible barrier was really a fluid dynamics crisis. Part 4. The hero moment, the bullet with wings. The solution didn't come from aircraft. It came from ballistics. Researchers studied .50 caliber bullets, which were already traveling supersonic. Their shape? Long, slender, smooth, minimal frontal area. The National Advisory Committee for Aeronautics concluded that the aircraft must mimic a bullet. Thus, the Bell X-1 was born. Key innovations. Extremely thin, unswept wings. .50 caliber bullet fuselage shape. all-moving horizontal stabilizer. The last one was critical. Instead of hinged elevators, the entire tailplane rotated. Why? Because shockwaves rendered traditional elevators ineffective. An all-moving tail could generate force even in disturbed airflow. Visual, exploded diagram of stabilator mechanism. This single decision solved control reversal. Part 5. Materials science under stress. At Mach 1.06, dynamic pressure loads spike. Even before sustained heating becomes an issue, structural stresses climb. Aluminum alloys of the 1940s were limited in fatigue resistance. Engineers had to overbuild the structure. But overbuilding means weight, and weight increases required thrust. This is the eternal engineering loop. The X-1 was rocket-powered using liquid oxygen and alcohol. It was not runway-launched. It was dropped from a bomber. Why? Because rockets are inefficient at low speeds. They're powerful, but short-lived. Visual, specific impulse comparison, rocket versus turbojet. On October 14, 1947, piloted by Chuck Yeager, the X-1 reached Mach 1.06. The sound barrier wasn't shattered. It was misunderstood. If you love understanding how mega machines and structures really work, subscribe now, because every week, we explore the future of engineering. Part 6. The Trade-off FS. Breaking Mach 1 solved one problem. It introduced others. Fuel consumption. Wave drag dominates at supersonic speeds. Fuel burn increases dramatically. Supersonic cruise is inefficient. Sonic boom. Shockwaves coalesce into a pressure front. This creates the sonic boom. Visual. Shockwave cone extending to ground. It's not a one-time event. It's continuous. This made supersonic passenger travel controversial. When the Concorde entered service, it was restricted from flying supersonic over land in many countries. Speed was possible. Economics were not. Part 7. Why swept wings changed everything. The X-1 proved Mach 1 was possible, but it wasn't practical. The next breakthrough? Swept wings. If a wing is swept back 35 degrees, airflow sees only the perpendicular component of velocity. Effective Mach number reduces. Visual, vector diagram breaking velocity into components. This delays shock formation. Aircraft like the F-86 Sabre exploited this. Swept wings made transonic flight manageable, but they reduce low-speed lift, which means longer runways, which means heavier landing gear. Every solution introduces compromise. Part 8. Debunking the barrier. There was never a literal wall. The sound barrier was a region of unstable aerodynamic transition. Physics did not prohibit it. Materials and control systems limited it. Modern aircraft pass Mach 1 routinely, but they don't do it economically. That's the real barrier. Part 9. Economic reality. Let's compare. A subsonic jet cruises around Mach 0.85. A supersonic jet cruises around Mach 2. Time saved on a transatlantic flight. Roughly 3 to 4 hours. Fuel burned? Often more than double per passenger. Visual, bar graph, fuel per passenger mile. Airlines operate on thin margins. Speed doesn't pay. Efficiency does. That's why modern airliners prioritize high-bypass turbofans and winglets. Not Mach 2. Final verdict. Was it ever impossible? The Bell X-1 didn't defy physics. It respected physics more deeply than anyone before it. It embraced shockwave theory, control surface redesign, structural reinforcement, rocket propulsion trade-offs. It proved that nature does not forbid supersonic flight, but nature charges interest. Fuel, heat, noise, stress. The plane that was never supposed to fly became proof that limits are rarely absolute. They are usually equations waiting to be understood. And once understood, they can be engineered around, but never eliminated. Because in aviation, as in all engineering, you are not fighting the air. You are negotiating with it.